Okay, hi everyone. My name is Alex Hamer, and today I'll be talking about how to get crowds from Houdini to Unreal. Firstly, a little bit about me. I'm currently working at SideFX in marketing as an FX intern, and I also previously worked for SideFX during my master's on an open world tech demo, which SideFX made called Project Pegasus, which is what you see here. And on this project, I made some real-time cloudscaping tools for Unreal. Okay. What I worked on at my time at SideFX so far was an extension to Project Grot, which was an already completed tech demo made by Simon Verstraete and others in collaboration with SideFX. But what was I going to add to this project? Well, we decided on crowds, as it would be a good way to add a more alive and dynamic feel to the environment. As well as this, SideFX frequently gets questions from studios about the best way to go about the crowds pipeline. There's many different ways to do it, and it's not really a solved problem, so to speak. And I'm also a guinea pig for SideFX, apparently. We had a few ideas for this mystical-looking alien cave scene, but we landed on bats, as flying agents are always fun to do. And also, given the size of the scene, we couldn't do something like dragons. And also, bats are very cute. These are some pictures I took on holiday recently. What we want to make is a tool where a user can draw a curve, input some points, and then it spawns the crowd simulation within the scene. Super simple. To be very clear before I start this presentation, though, whilst this project has completed its main cycle, we will still be continuing research throughout the rest of my internship, and this is not the final call for what I've created. And here's some other bats from the same trip. So here's how our tool works. This video is sped up, obviously, because, we open it up, we spawn a HDA, we can then draw the curve and place points to where they're going to flock, for example. And yeah, I do that for a few seconds. Then we can head to the sequence tab and set up what they're going to do in the scene, and then I can simulate and export the agents in a second. There you go, it does all of that. Then we can re-import them into Unreal. And then we can bind them to a sequencer. And then the result of that is, hopefully sound works. Oh. Okay. So here is more of a breakdown of the goals. Firstly, we want to create a tool which can procedurally create Houdini crowds and bring them into Unreal, obviously. Another main goal is to have the end user never leave the engine. And this could be useful in applications where you're a technical artist, making tools for a level designer. And this is helpful because when you're trying to make rapid additions or changes to a level, flipping between programs constantly can be limiting and frustrating. So we're just reducing the complexity of the workflow. Because of this goal, though, we're limiting a Houdini tool to be inside another program. And because of that, we want to design a custom interface for HDA to only expose the information that we need. With the goals laid out, let's talk about the challenges. The obvious one being that Unreal is primarily a real-time game engine, and we need an optimized solution where we are conscious of variables such as bone count for our agents or polygon count and texture size, as these all impact performance. So the goal that games are generally aiming for is 60 frames a second, so we need to make it as optimized as possible, as we cannot rely on offline rendering to do the work for us. Currently in Unreal, we have access to this handy feature called Nanite, which is essentially a virtualized geometry system, which splits a mesh into clusters, which are then put in a hierarchy and rendered at different resolutions based on camera distance. It's a bit of an oversimplification, but for the presentation, that's the idea. This can be extremely useful because when you have a very detailed mesh like that one in the top right, which is 2.5 million triangles, you can actually render hundreds of these in a scene at a small cost. However, notably, as of Unreal 5.4, this is only for static geometry and cannot be used on skeletal meshes, so characters. The next challenge is that it's a game environment, so we have to assume that the camera will not be controlled by us, but instead a random player. Because of this, the final result has to be perfect from all angles, and we cannot rely on a controlled view to hide any imperfections. As a byproduct of this, we have to think about how the crowd agents enter and exit the scene during runtime. They can't just pop into existence at the back of the cave, because at that exact moment, a player may be looking there. Finally, this ended up being a fairly advanced tool, even if it utilizes simple concepts, and there's just a lot of different components to it. And it's just the reality that mixing two pieces of software is never 100% a smooth process. So making sure that the end user doesn't suffer because of the complexity was one of the biggest challenges. So we have our plan finished with our goals and challenges, but before we can talk about crowd simulation, we first have to talk about Unreal, because the main point is to build a tool for Unreal. So it's important to talk about why we do certain things. We need to get data from Unreal, such as what our scene is like and where our curve is, for example. And we can't just jump straight into simulating without having any information about where the bats should go. So firstly, as mentioned, we need to create a custom interface for our HDA, and we can do that with editor scripting. Editor scripting can be a blanket term for automating tasks or creating in-engine tools. There's currently two main types: scriptable tools, which are very viewport-orientated, similar to something like the landscape editor mode, but it has limited UI customizability. And then there's editor utility widgets, which is what I ended up going with. This is for more parameter-heavy use cases, which don't require the viewport to be interacted with, and it's similar to construction scripts, which is an Unreal thing, which is the video on the right. And we can use these to create a custom interface for our HDA, but for someone unfamiliar with Unreal, you may not know how it currently works when you use a HDA. So when you drag a HDA into the scene, it creates a panel where we can manipulate the HDA by baking the geometry output, setting inputs and parameters, etc. And this will all make sense for someone who's a Houdini user, but not for a noob. Here's an even more complex HDA example with multiple inputs, parameters, and a PDG network. And you can quickly see that it requires a lot of scrolling to interact with this menu, and again, even more technical information, which in most cases your designer will not need. So let's go about solving this. To create an editor utility widget, which is essentially just an editor menu, we can use this widget designer. We can add various functionality to it, such as buttons or property editors, tick boxes. And if you've ever used Unreal, you may recognize this as it's the exact same widget editor, which you use for in-game menus. But once we've designed what will be in our menu, if you can see in the top right, we are in designer mode. If we flip over to the graph editor mode, we can add blueprint and code functionality to our buttons and such. So to make this able to control the HDA, though, we need to use the Houdini Engine Public API, which adds blueprint functionality to our editor, Houdini blueprint functionality to our editor. With this, we can instantiate assets, essentially place them in the world, control a Houdini session, set all various types of inputs on a HDA, which you should recognize from Unreal, from Houdini, and control PDG networks. So whilst going through this and creating a custom interface for the HDA has all of the advantages that I mentioned, such as simplicity for the end user and only showing the information you need, it can still be time-consuming and tedious to set up, and I would advise people to think about how useful it would be for your scenario if you intend to do this. So we have our tool interface, but we have a little ways to go still. We need to find a way to feed data from our scene to our simulation. This could be things such as collision data, so our agents can avoid stuff, or knowing where to flock or which curve to follow. So within HDAs in Unreal, there's currently three types of inputs that you can feed into the HDA. So firstly, geometry inputs, so any asset in the project directory, such as a static mesh. Secondly, a Houdini curve inside Unreal. And finally, a world input, which is essentially any actor or asset placed in the level currently. These are all the different types of assets you can put into a HDA as of 20.5 and Unreal 5.4. There's a lot to see here, and you don't need to worry about these. But the one that I'd like to draw attention to is data tables. So data tables are a cheap way of storing data in a table-style format, and they can be used to store things such as gameplay data, so for example, values for your characters in different states, and they can be called upon during runtime, but notably not edited during runtime. So let me talk about an actual reason to use these things so you can understand why they're useful in the context of Project Grot. In my CrowdSim setup, I sometimes have them start with the agents hanging upside down from geometry, but the trouble is how and where do I generate these points with the tool? The scene is made of dozens of highly detailed meshes, and how do I send all of those meshes over, then highlight specific areas based on the original Unreal viewport view, and then generate points based off that? And then how do I do that without causing significant performance drag? Well, the answer is I don't. My solution was to use blueprints within the tool to generate points from the current editor view, again contributing to this never leave the engine idea. So we simply use a raycast or a line trace as it's called in Unreal to splatter points from the current view, and then add them to an array of points and normals. We can then input this data table into our HDA, and after a little wrangling, we can get them as points with normals that Houdini recognizes, and we can put our agents on. Another main example of their use is that CrowdSim requires geometry input to know where not to collide with and what to avoid. So we can't just have bats going through walls as it's a small scene and will be very noticeable. So we need to find a way to send a low-resolution version of our scene to the HDA, because as mentioned, it's made of lots of different meshes that are extremely detailed, and we don't need detail for collision. My initial idea was to use the nanite fallback mesh, and this is essentially a normal resolution mesh when nanite isn't supported. This turns a mesh of about 2.5 million triangles to about 39,000, which is more approachable, obviously. And we can do this simply by telling our HCA to use the mesh instead on this mesh instead on our input settings. Or I could have used the even lower resolution collision geometry, and you can see it peeking through here in the purple. However, as of 20.5, RFE is pending. We still have to send the whole nanite mesh to even use this collision data, so I needed a better solution. An idea that I came up with early on was to make a curve which goes where the path of the bats will be within the scene. We then somehow sweep along this curve, which is the blue, and whenever we intersect with a mesh, we grab the geometry from it, which is the green, and then using those points, we store them in a data table and recreate them in Houdini to be a mesh that the agents avoid, which is purple. Whilst this may have been possible to achieve in some sort of blueprint or editor tool, it turns out that PCG was the most efficient way to go about it. So PCG, if you're unaware, is Unreal's toolset for creating procedural generation content, and it gives you access to previous existing world-building pipeline tools, such as landscape splines. And this, as they say, blurs the lines between procedural and more traditional workflows. Of course, it's a node-based system, so I'll briefly describe my setup. We are spline our curve, and we sample points along it. We then modify the bounds of each point. Basically, we make a bounding box around each point. Then we use this bounding shape in a volumetric query, which is a voxel query, and this is what the voxel query looks like against some basic shapes. Then, as I said, we use the bounding shape of the spline to only use the points that are within that bounding box. And here's the final result. You can see that the green is the bounding box of the spline, and you can also see when it goes near a mesh, it grabs the voxel data position and logs them. This turned out to be even more optimized than my initial idea, which was to grab the actual nanite fallback mesh polygons when we sweep. But with voxels, we can still get an accurate representation of our mesh without any of the details, because when the bats are set up to avoid stuff, they don't go within a certain distance of any geometry anyways. Here's the tool in use in the grot scene. That's pretty much it. We then take these points into Houdini and recreate the scene by turning them into voxels again, basically just add cubes. Then we could just smooth them out with VDBs. So we could have this system do this draw the path method every time we do our setup if we were going through a much larger environment. However, if we had a small scene like grots, we could use this same PCG setup to sample the entire scene at once and just have this pre-baked collision data. So let's recap. We're taking our start and end location points, as well as the world geometry, and feeding it into our HCA via data tables. And I didn't talk about this, but you might have seen it during the demo, but we use an Unreal spline to draw a curve, which we pass via world input, and as well as the flock location, which you can just pass to the HCA. And then this all goes into our simulation. So now we have our interface, and we also have a way to tell our simulation what it's meant to do within the scene. Since we're at a Houdini event, I suppose we should talk a bit about Houdini. I'm also in marketing, so I suppose that is my job. Of course, I am doing crowd simulation tool, but why would you want to simulate crowds? Well, because it's really, really exciting. In a typical crowd simulation in Houdini, we have our states, which define the behavior of agents when they're in Z state. We then have triggers, which move the agents between different states. Also attached to this, we have transitions, which handle the blending between different states. Then our agent and crowd source, which is what the agent is and where we spawn them. And then the solver, which puts it all together. This is pretty simple in concept, but very quickly you can build extremely complex and dynamic crowd simulations. You can see here is my earliest working version. And then this is my final version with 28 states and 30 triggers. And this is why it's important to have a very beautiful node graph like me, so you actually know what's going on. As a side note, different colors represent different states in the examples that I show in this presentation. I found that color coding my agents was a very good way to visualize and debug the behavior of them. With my simulation, I didn't actually use anything new. There are recent additions to the CrowdSim toolkit, such as motion paths, but I found that with the regular solver setup, I was able to achieve what I needed, and that it was more suited for flying agents. So what is so special about my crowd simulation? Well, I wanted to achieve procedural sequencing. Essentially, what I mean by that is that I split my simulation to contain an intro, so how they enter the scene, a task, so what they do, and an outro, so how they leave the scene. If you remember at the beginning, I mentioned one of the challenges was that because the simulation can be viewed from any angle, it's important to think about how they enter and exit. So I'll go through some of the different ones now. So first, the intros, the way they enter the scene is either already mid-flight or they're sleeping on the cave ceiling. Then here are some of the task options. So flocking out a location, flocking and then following a curve, or just following a curve. And then here are the ways that they can leave the scene, either just ending the animation and stopping if they are out of view entirely, or they just go back to sleep on the cave ceiling. To achieve this, I need to set up my trigger network so that it contained many if switches, which switch to different trigger setups based on the input, and you can see that here. Here are some examples of different combinations, and I'll give you a second to look at that so I can drink. Okay, hopefully you've seen a few. It may not seem like many options, but you can have all of these different combinations, which allow for many unique setups. A useful side effect of having this procedural sequencing is that within the menu, I only needed to show the parameters for the current setup and hide the rest. For example, if I were having the bat start mid-flight, I wouldn't need to show controls for how long they were sleeping and where they would be sleeping. So it's a nice way to declutter and simplify the menu. As you can see here in this video, it only shows the tabs relevant to the current setup. So we have our procedural sequences, but now let's break down some of the art direction for how I wanted the bats to behave. Within their main flight cycle, so following the curve, I chose to have 3 states and base them on the vertical velocity of the agent. So firstly, flapping their wings, which is sort of their default state. Then we have diving, which is the state that I use when they're going downwards at a high rate. Then we have gliding, which is when they're moving between diving and flapping their wings, or if they're traveling downwards at shallower angles. It's worth noting that these are just cosmetic states. The actual behavior does not change. We just use different states to control the animation, as for the most part, one state has one animation. To make this work, I used a crowd trigger setup, but I set it to use a Vexpression, in which I basically detect the vertical velocity of the agents, and then, depending on the range that we're in, I move to the specified state. Here's a demo of what this looks like in action. You can see that they're usually flapping their wings, and then when they move downwards, they either dive or glide. And I did this for my main flight cycle, as just having them constantly flapping their wings just didn't feel natural enough. Yeah. We also want to introduce some variation in our bats, which is a common thing with crowds, where you don't want every single one to be identical. And you can do this in the crowd source outside of our dot network, in which you can set randomized agent primitives, scale, velocity, and more. And I wanted to introduce some random scale to my bats, but I found that this made the smaller ones slower naturally. However, this tended to destroy the flocking behavior and cohesion of the bats that I had built. So I ended up randomizing the p-scale of the agents just after the crowd sim setup, and that worked fine. This was a common theme whilst building this simulation, was that even smaller changes would require large amounts of time spent balancing all the forces and numbers for all the different states. And for anyone who's worked with crowds before, this will be familiar, as you know that they can be extremely hard to control sometimes. But this is also just the case with simulation in general. So finished with our sim, but it's important to remember that crowd simulation is basically the same as particle simulation. So you can most of the time manipulate them as if they were particles, as you just saw with the point scale example. Before I move on, I'll briefly go over my HDA setup. It's pretty simple. So on the left, we have our curve input, which I take the curve from Unreal, smooth it out, and also get the location of the starting and end point for later use. Then the world geometry, which is in yellow, which we then feed into our crowd sim in the green. Our agent setup is the blue, which has our source points, our clip properties, and our transition graphs. And then the sleeping points on the far right for when we want to land on the cave ceiling. And then down at the bottom, after the simulation, we split it up and either export with Skeletal Animation or Nigra and that, and I'll get into those shortly. So we're at a point now with our tool interface and our input and our working crowd simulation, but now we need to think about bringing it back into Unreal. We have our tool, which gives our digital asset data, then Houdini Engine runs our HDA, which does our sim, and now we need to figure out different formats which we'll use to transfer the data to Unreal. I chose Vertex Animation and FBX Animation, so Skeletal Animation. So let me describe some of those. So Skeletal Animation, so an FBX animation, is a way of animating a mesh which uses a bone structure. Our animation controls the movement and rotation of bones, which by weighted influences to the vertices around it, deforms the mesh, and this is the standard for games currently. Vertex Animation Textures is a way of storing animation data in textures, and then we apply this texture data to the vertices in real time, allowing for efficient rendering. So first, let's go over skeletal animation. If you know anything about skeletal animation in games, you may be wondering why I even tried. Traditionally, skeletal meshes are reserved for your player characters or high-importance non-player characters that require it. They can still be used for background characters, but often a way tuned-down version. Well, the reason I tried was that this was first and foremost a research project, so I wanted to see how it would fare in a scene such as this, and I also needed something to compare my more efficient techniques against. The thing with skeletal animation, though, is that I couldn't just export 100 bats with one render operator. Unfortunately, it's not that simple. I needed a way of splitting each agent up into its own pocket dimension, and then just exporting itself and not the other agents, and we also needed a way to automate this. We can use PDG or TOPS, which if you've never used it before, is a network type in Houdini, which allows you to build word generation recipes and create partitions and dependencies between different items. The TLDR of this is that we can use it to automate our exporting so that we export each one separately and wait for that item to be finished before we move on to the next. To split each agent up into its own pocket dimension, we use a split node, where we can set the group to be a wedge attribute. Then we can get the specific agent based on which pocket dimension we're currently in, and then unpack the agent, configure some more stuff, and then output it as an FBX. Within our top net, we have our wedge node, and then after every time we've rendered a new FBX animation with the ROP fetch, we just increment the wedge value and move on to the next item. So we can control our top net in Unreal, as mentioned earlier with the Blueprint API. But a problem that I had was I wasn't able to detect the status of work items within my editor menu. You can see the status of them with Houdini Engine in the details panel, but again, we're designing a system so that the user doesn't ever have to leave it. There isn't just a function where you can ask the API how many PDG items are cooking, and yes, there is an RFE for it. So what I did instead was make a Python script which checks in the export folder how many files are starting with the export name, and then this can be used to gather our progress to tell the user when the exporting is done. And here's a quick demo of this. We click simulate, it does the simulation, and then it checks every second on our progress, as you can see on the left. Sorry if you're at the back. And once it's done, it lets us know that we've completed. And this is because visual feedback is very important, especially for someone who's unfamiliar with how the tool works. So now we have a way to export each agent separately, and we need to think about how to get it into Unreal. Within Unreal, a skeletal mesh is actually made up of a few things. We have our physics asset, which defines the physics for our mesh, which you could use for things like ragdolls. Our skeleton, which is our bone hierarchy. Our skeletal mesh, which is what we use in the scene, which contains even more information. And then to top it off, most of the time we'll be applying an animation to all of these. These aren't really important for this presentation, but the point I'm trying to make is that each frame we're having to deal with these and update them. So what I decided to do in my use of skeletal animations is to have the FBX animation handle both the animation of the agent as well as its position using the locomotion bone. And this way I didn't have to deal with any other techniques to mix in. I could simply use the FBX files as they were. This obviously brought up some issues, though. I'll talk about some of these. Firstly, when I put them in the scene, they would be flickering a lot. And this was because of the fact that I was moving them, as I said, with the animation instead of another way. To fix this, I needed to change the bounds in the skeletal mesh component. And this allows the position offset of the vertices to be rendered outside of their normal bounds. The side effect of this, though, is that it will reduce performance and shadow quality, which is why I made sure that I set it to be the minimum that I needed it for it to work. This is definitely not the best solution at all, but for such a small scene, it would be passable. The second main issue that I ran into is that in Unreal, for the sake of optimized and efficient loading and processing, encodes every file that you put into the project into a UAsset file. The trouble comes when you want to import hundreds of animations at once, as currently each time you import an animation, you have to select a skeleton which it will bind to. Also, our PDG network does not export to this UAsset type, so I needed to find a way to automate this. I ended up using another Python script, which took all of the matching names and numbers and auto-imports them and also auto-binds the skeleton. So yeah, it just goes through and it just does all of it for me, which was really nice. So it's actually now possible with the Houdini engine for Unreal plugin to export directly to animation sequences, and this bypasses the need for this script. So this process is now all simplified. However, this is new as of 20.5, and I started the project whilst the dev cycle was still going on, so this is why I didn't use it. And I also didn't have access to the KineFX file, as we used an external contractor for the animations. This one is less of an issue and more of just what I needed. I couldn't just plop all of these skeletons within the scene and have them constantly acting on their own. It's messy with hundreds of them, and I wanted finer control over when they did their thing. So in Unreal, we have sequences, which is a tool for creating controlled cinematics of game sequences with a timeline. You can set up camera shots and audio and the typical stuff you'll see in cinematics, but more importantly, you can attach actors within the scene and have them call events on them and do stuff with them. Level sequences are quite versatile because while you can use them for pre-rendered cinematics like this, you can also use them for real-time game sequences for level. And this is a cute little indie game called Billy Bust Up. Thank you for them for letting me use them as an example. So this is a music-based level, and the sequencer is controlling it in real time. course, I needed a way to automate adding my skeletons to the sequencer because I had hundreds of them. I didn't initially use blueprints. I think I was feeling a little bored of blueprints at the time, so I ended up writing some custom C++ functions which combine these skeletal animations to the sequence. And this works super well, but unfortunately, when you add C++ to an Unreal project, it sort of dirties the project and means that if people want to download it and look at the tool, they have to download Visual Studio and all this other stuff. So I had to just translate it to blueprints, and it works fine. So just making it harder for myself, essentially. So now I could use the sequences to control when the bats start doing their thing. So we have our first technique set up, a way to spawn it and within the scene and control it. So now we have a good baseline for something to compare other techniques to. So the next method I used was Vertex Animation textures. It may be hard to understand what's actually going on in this image, and I don't blame you, so let me break down how it works. Essentially, each column in the vertex texture is a vertex index, and each row is a frame. Each pixel has its RGB values turned into translational XYZ values, which are then applied to the vertex index at the specific frame. For example, this pixel here is telling vertex 16 at frame 3 to move on the x-axis by 97, the y by 252, and the z by 127. And then in the vertex shader, we read this back as a texture, read this texture back, and then apply the offset to the vertices in real time. Why would you do this? Well, there are various cool benefits. They're compact, meaning instead of storing expensive animation data in skeletal animations such as bone weights, bone indices, animation keyframes, which when you have a super complex animation with many bones, it can take a lot of memory. Instead, we just use a texture. You can also combine multiple animations into one texture, as you can see here in this example. And because of this, the engine only has to work up to call this texture once, which is obviously more performant. They're also a highly performant way of handling pre-baked complex animations, which would fail to run in real time, and I'll talk about some examples shortly. But of course, every method is not without its complications. As mentioned, one column is one vertex and one row is one frame, so there are resolution limits. You may struggle in some scenarios where you have extremely detailed meshes at high frame rates. Also, because they're pre-calculated in Houdini, they're not easily changeable once they're in engine. There are scenarios where you could use them in interactive ways, like having them play the animation when you get close, but this obviously requires extra setup. They're notably only a visual-only shader most of the time. We're telling the GPU to move the vertices in the final view, not the actual geometry, and because of this, things like collision are not practical. There are some ways to get around this, as I just mentioned, but this is another thing and requires even more setup. Finally, it can be complex logistically to sort out some issues, such as setting up level of detail, lighting, etc. So this may sound like a lot of downfalls compared to advantages, but if used correctly, there's no better solution than Vertex Animation textures, and I'll go over some common uses for them. Crowds obviously are a good one. You can fit a lot of variation, which is what you want for crowds at a small cost. Example is by Mo at SideFX Labs, who made a tutorial on crowds in Unreal using Vertex Animation textures. And you can see here there's a large amount of variation. As mentioned earlier, dynamic simulations which wouldn't be possible with bones, such as rigid and soft body dynamics, fluid simulations, cloth simulations, and particle simulations. Grass also is more of a common version of it. This is an example by Yumna Sahab, who is an intern at Labs, where with Grass, you apply vertex offset to simulate things like wind. This is more of an example of vertex animation as opposed to vertex animation textures, but the principle is the same. So this basically gives you the idea of what they are, but this is not the whole story for how they were used in the project. Whilst I originally thought of having the vertex animation textures handle both the position and animation of the bats, this would have resulted in each agent requiring its own high-resolution texture for their unique path within the scene, meaning that if I created 100, I would have to import 100 textures, and for obvious reasons, this isn't practical. So I needed something else to handle the movement of the bats, and for Vertex Animation to handle the animations. Whilst there were a couple of initial ideas, I ended up going with Nigra, which I'll get to shortly. But first, let me talk about how I use Vertex Animation for the animations. What I needed to make was a Vertex Animation texture with all of the different possible animations in our simulation blended into it. So I created a crowd simulation with a single agent, but instead I just looped through each animation once. And this is what this looks like. Yeah. To make this blended animation into a texture into Houdini, we unpack the crowd sim and turn it into polygons and then do a little cleanup. And then we export with soft body deformation mode, which is a mode where we have consistent topologies, we just deform them. Some other modes which are interesting to talk about, rigid body dynamics, which is for packed pieces of geometry with simulation data, dynamic remeshing, which is for surfaces which are remeshed every frame with dynamic topologies, and finally particle sprites, which are just for points with simulation data. Once our ROP node is done, it spits out this special and weird looking mesh, which I don't actually know why it looks like that. But we apply the texture to it, and then of course we get our Vertex Animation texture. We then apply this texture to a mesh within the shader using a handy material function we get from the Labs Unreal plugin, and then it works. It plays through all of our animations just as it did in Houdini. This material function also gives us some nice quality of life advantages such as interpolation between frames or compressed normals. So we have our Vertex animation with all of our possible animations in Engine, but obviously we're only halfway there. So this little animal fun fact for you, bats actually move in real life. So we need to move the mesh like in our simulation, and then call different parts of the Vertex animation when we need it. This is where Nigra comes in. So Nigra is Unreal's primary visual effects and particle system editor. It's made up of systems, emitters, and modules. It's a highly customizable and modular system where you can simply drag in modules or write your own. And with it, you can achieve simpler things such as snowfall, all the way up to advanced fluid and smoke simulations. Here's the interface. So the blue node is the system, which is what we put in the scene. And then the orange is the emitter, which is what we actually build our particles with. And it also has a Houdini plugin. To get our crowd sim in Nigra, we use the Nigra ROP from the Labs toolkit and input our crowd sim. And if you recall, I mentioned earlier how crowd simulations are nearly the same as particle simulation. So what this node does is take the position of agents as if they were only particles. This gives us a point cache, which is essentially a JSON type file, which contains all of our particle attributes over a frame range. So we also helpfully have a working example of a point cache emitter in the Houdini Nigra and plugin folder. So we just plug in our point cache data, and then straight away, it works. We have our meshes moving position-wise, just like in our simulation, but you'll immediately notice they aren't doing any animations and they're not orienting in any direction. Well, this is because crowd simulation uses the orient attribute for the agent's rotation, but the Nigra mesh orientation module doesn't support using quaternions currently. So I just made my own Scratch module where I set the mesh rotation quaternion value directly. So now they're fixed and orienting as they should be. But again, still not playing the animations, so let's move on to that. So we've got our agents moving in the scene with Nigra, but now we need to call upon our blended animation that we made. So we have our blended animation, but what we need is a way to select and move through frames based on the current state's animation. We have our Vertex animation, and we have the values for where each animation starts frame-wise. So what we need to figure out is where each agent's current frame in that animation is, and we do that using this little wrangle here in our original simulation, which stores this value as a frame number. Then before we export to Nigra, we need to find an attribute from this point cache, which we can just steal, which just goes unused. I didn't use any color or alpha value, so I just stole alpha. Then after our simulation, we use a wrangle in which every frame we check what state we're in, and then we set the alpha to be the beginning frame of that specific state's animation. And I am aware of how ugly that wrangle looks. Then after this, we check how far we are in the current animation clip, using that wrangle inside the simulation that I mentioned earlier, and then move us forward however far we are. In Nigra, the final step is to just pass this to our Vertex animation material by adding a module to set the dynamic material parameters and passing the Houdini alpha value to it. And then it works. Our meshes are moving and playing the correct animation at the correct time. But you might notice, especially near the end of this, that they seem to be stuttering a lot for some reason. Well, it's actually because while they are playing the correct animation at the correct time, they aren't set up to blend between different animations yet. Well, I couldn't just interpolate between state meshes. This may work for something when the animations are only slightly different, like here with flapping their wings or gliding. But for something vastly different, the animations just go through themselves. So I needed to find a different way to do the transitions. To have exact and smooth transitions, I needed to extend my original blended animation to include set blended transitions, and then choose these when I needed them. The problem that I encountered immediately, though, was that if we were already halfway through, let's say, the flapping of the wings animation, we're then setting it back to the beginning to transitions to a new state, which obviously created noticeable jitter. I needed to make it so that in my simulation, we finish playing our animation in full, and only then can we move to a new state so that all the animations would sync up. To make this functionality possible, it turned out I needed to use the clip transition graph. This is a node outside of our simulation network in which we can declare how various transitions would work. We can use it to delay transitions until an appropriate point in the current animation clip, or make use of intermediate clips and blending information. But I did not have this set up with any part of my simulation, and I was just using the inbuilt blending, so I needed to change my whole setup to do this a week before the Horizons event. So after getting a little upset, I went through all my transition nodes and tweaked them to do this, and adjusted my simulation to account for these new timings. Another problem that I encountered was that I needed to make the blended transitions even for animations that I didn't have, because I didn't ask the animator for, because I didn't anticipate having to do this. And as mentioned way earlier, I didn't have access to the original KineFX file. So I needed to find a way to make nice blends between my looping states. And for this, I ended up using KineFX to blend smoothly between transitions. After implementing this, hopefully you can see that they aren't cutting between animations. Maybe a little hard to see on this GIF, but trust me, they aren't. And here's what they look like in the scene. So we made it to the end of the pipeline. We have our tool, like how you saw at the beginning of the presentation. We have two working methods where we can enter the menu, choose which mode, and put them in the scene. Now, the obvious question is, now that these two methods are done, which is better? Well, hopefully by the way I describe both of them, you may have guessed that Vertex Animation with Nigra is way more performance. But in a production, for the final result may matter most, but time making the tool also matters. So to more closely break down which more is suitable, I chose to think about three categories. So ease of setup, ease of getting the agents into the scene, and obviously performance. In terms of ease of setup, it was hard to say. With Skeletal animation, the main tasks were easier to do because I just had a ROP node, but there were many extra hurdles to jump through, such as custom import scripts, for example. But as I mentioned, there are movements being made with the KineFX to animation sequence pipeline. So hopefully in the future, things may become easier. With VAT and Nigra, the setup itself was super quick and easy, and I actually surprised myself with how intuitive it was to set up. I had set out a whole week to work on it, and I ended up getting the first iteration done in one afternoon. Keep in mind though, I still had the basis of all the data input that I'd set up with the tool whilst I was doing the skeletal animation method. Next, ease of getting them in the scene. With that, we have our blended animation. Once we have our blended animation mesh and texture in our project, we don't have to re-export it every time. We can just reuse it. So every time we make a new sequence, we just need to make a new point cache, which takes about a minute and is a very low file size, and it's just a JSON file, which I talked about. With skeletal animation, it's a different story. It takes a while longer. And I think about with 100 bats at 1500 frames, it took about 10 minutes for all of them. And we have a separate file for each one, and no one wants this. This could be maybe useful for cinematics or something, but it's impractical with most game scenarios where you have one file for each animation. For performance, VAT easily surpasses expectations. I could put up to 8,000 bats in the scene and only drop around 10 frames, and they're clearly very lightweight. On the other hand, skeletal animation is very limited by the amount of agents. This could be useful still for smaller scale scenarios such as this scene, and this model also only had 50 bones and about 9,000 polygons, so there was still a lot of wiggle room for even more optimized skeletal agents. On a PC, you may be fine without about 100 bats, but once you start adding more and more, it appears to have an exponential fall-off. And bones are the main culprit for this. Bones are not practical for crowd simulation unless you have a very harsh level of detail setup, and you just have to jump through other hoops. These numbers, like 10 minutes, 1 minute, whatever, they aren't much to go by. And of course, this will run different on various systems and platforms. So the thing is, as mentioned at the beginning of the project, whilst it has completed its main cycle, it's still in progress. And I plan to do a more detailed performance review when I release the project in November when my internship ends. Full disclosure, I didn't make the bats. They were modeled by a very talented modeler named Alex Nowitzki. And then it was rigged and animated using KineFX with Apex by another very talented animator named Bogdan Lazar. And these are some of the extremely cool people I'd like to thank who got me here today and helped on this project. So Fiona, who let me work at SideFX and being the best mentor I could have asked for. George introducing me to Houdini at university and teaching me what it means to be a tech artist. Maya for coming in clutch with help and guidance. Simon for giving me a handshake as well as guidance. And the Pegasus team, so Ian, Flyker, and Tillman for helping me through my first commercial project. And then Cameron and Damien for crowds and Unreal help. And finally, the other interns for support. Thanks for listening. Here's my email or contacts, and questions.